you seeing my screen?
I am, yep, and it looks perfect.
Okay, it's working. I always have trouble with Zoom, but it looks like it's going to work. Okay, I'm going to talk about mean squared errors of X-11 filters. Starting my own timer here. To give a little background for some who may not be familiar with this, when time series modeling was developing, people began thinking about, for seasonal models in particular, how it compared with X-11 seasonal adjustment. And in particular, how would X-11 filters compare with signal extraction filters from stochastic time series models? And the first person that looked into this was Bill Cleveland in his PhD thesis. Bill had a long career at the Federal Reserve Board. And then he and his advisor, George Tiao, had a JASA paper in '76. And the result of the work was models that would produce signal extraction filters that approximated the default X-11 seasonal adjustment and trend filters. Excuse me. And other people followed, trying other models to get closer approximations, Bird and Wallace and James Chu. And the models that were used there were aimed at just approximating the X-11 filters. They did not look like models anybody was using in practice to model series. And so Planas and Depito then in 2002 did the same kind of approximation thing, but they restricted their model form to the airline model with canonical decomposition. So that was something people were actually using and sort of more practically useful. And then in '98, Depito and Planas had a paper where they turned the question around. They looked at choosing X-11 filters to approximate model-based signal extraction filters. So again, they focused on the airline model and canonical decomposition. And for specific airline model parameters, they looked at what X-11 filter options, the moving averages, would minimize the sum of squared differences of the filter weights from the two. And they did it for both the seasonal adjustment, the non-seasonal, and the trend components. So all that is fine, but all that the work to that point had concentrated on differences in the filter weights, and there are a lot of filter weights. So it sort of left open the question of, well, do small differences in a lot of filter weights matter? And so Jane Chu, who was a student of George Tiao, and I, Jane was looking into this in her thesis, and we did a couple of papers. And what we did that was different, it was somewhat mimicking what Depito and Planas did. We were looking for X-11 filters to approximate airline model canonical decomposition filters. But our criterion wasn't the squared differences in filter weights. It was minimizing the mean squared error of the X-11 estimates. And in the papers, it was for the non-seasonal component, just for seasonal adjustment. We didn't consider doing this at the time for trend estimates. We wound up with X-11 filter choices that were very, very similar to those of Depito and Planas. But what it gave us was a measure of how much worse would you do if the true situation were an airline model and canonical components, and you used an X-11 filter. How much worse would you do if you made the best X-11 filter choice? And we computed it for other filter choices. And there have been some enhancements in this direction by Jonathan Wright and Osbert Tang and Brian Mansell and I that are still in progress on this. So what we didn't cover in the previous papers was trend estimates, and that's what I'm going to focus on here. So the models that well, there are two ways that I'm going to approach this, that I have approached it. One was to use just models for a non-seasonal series where the trend and irregular components followed models that came out of the canonical decomposition of the airline model. This is a bit simpler than doing it for the full seasonal series. But I also did it for monthly seasonal series, and I'm showing the models there. I'm going to focus on the trend models. And I would note that the general form of the trend model with the second difference and potentially a moving average component have been widely used. I've got some references there. And two that may not be expected are that this model sort of underlies the Hodrick-Prescott filter that's been widely used. And it was also sort of corresponds to work that Whitaker did on actuarial graduation 100 years ago. So as I said, I'm going to take trend and I'm going to take component models from canonical decomposition of the airline model, varying the airline model parameters theta 1 and theta 12. The innovation variance doesn't, it's just a scale factor, so that's fixed at 1. So there's the form of the canonical trend model. And let me point out a couple things about this that actually I hadn't really looked for and kind of noticed yesterday, added it to the talk. One is that it's of this form. It's an O22, but a particular form where the MA has this 1 plus B factor. And so that leaves another factor, MA1 factor. And then it turns out that this coefficient in this other MA1 factor is very close to the seasonal moving average parameter to the 12th root. Exceptions occur when the non-seasonal MA parameter gets beyond 0.8 about, and when the seasonal MA parameter is below about 0.2. Those are unusual cases. So most of the time, this relation holds. Also, because of this eta depends on the seasonal moving average parameter, but very little on the non-seasonal parameter. And in fact, it's high. It exceeds 0.83 for all these values of the seasonal MA parameter. I would point out, though, that the trend and irregular variances in their ratios do vary substantially with the theta 1 and theta 12. And it's the differences in these variances that are really driving the differences in the filters. So to compute the mean squared error of trend estimates from either the non-seasonal version of the model or the full seasonal version, and I'll show it here for the seasonal version, sort of goes like this. And I just want to point out one thing. So in the full version, we got the trend, seasonal, and regular components. And suppose omega TB is the trend estimate filter. And this could be anything. It could be the model-based filter, the X-11 filter. It could be symmetric or asymmetric. But in any case, the error in the trend estimate then is given by this expression, which the contributions from the various components are this. What we'd like to do is compute the variance of this expression with 3 independent components, but we can't do that because the trend and the seasonal are non-stationary, so the variance isn't well defined. But if I sort of modify this expression to divide the filter by 1 minus b squared here for the trend, 1 minus the trend filter, so I apply it there, then this part is stationary. I do analogous thing with the seasonal. So from this expression, one could get at the mean squared error of the trend estimate if certain conditions are satisfied. So here's that expression again. The certain conditions are these, that this error becomes stationary if this 1 minus the trend filter contains a second difference. That's true for the model-based filters that would come up from any models with two differences. It's true for the X-11 symmetric filters. It's not true for the X-11 asymmetric filters. But if you get X-11 asymmetric filters, quote unquote, from the symmetric filters with full forecast extension, then it is true. So that's the nature of the asymmetric filters, the concurrent filters that I'm going to use. They were obtained this way. And the other condition is that the trend filter contains the seasonal summation operator. That always holds in practice. And actually, the MSE, I haven't computed directly from this. It's done a different way that's explained in one of our papers. So to determine which choice of Henderson moving averages minimize the mean squared error of trend estimates from X-11. So I said I use two approaches. One is to use the full seasonal model, and the other is just sort of the non-seasonal part of it. And that's somewhat simpler, and I wanted to see if how the results would compare. And this was done for airline models with their non-seasonal and seasonal MA parameters ranging from 0.1 to 0.9 and increments of 0.1. And the results here are going to focus on the mean squared error percentage difference, defined as shown here. It's 100 times the mean squared error of the X-11 trend estimate or the Henderson trend estimate for the non-seasonal model over the optimal model-based estimate mean squared error -1, so the percentage difference of these two. So now I'm going to show a whole lot of graphs. So let me explain the first one in some detail. These are mean squared error percentage differences for the non-seasonal model case. So it's just trend plus noise components. For the combinations of airline model parameters shown, so 0.2, 0.5, and 0.8. So there are actually 9 combinations. I'm only showing 0.5 and 0.8 for the seasonal moving average parameters. Why is that? Well, if you look at the 2 rows here, the 0.5 row and the 0.8 row look awfully similar, and the 0.2 row does as well. They aren't identical. You can spot differences, but they're very close, so you don't need to look at all of them. So let's look at the upper left graph here, where the non-seasonal MA parameter is 0.2. So on the horizontal axis, I have the Henderson MA possibilities, which ranged from 5 to 35. And the vertical axis shows this mean squared error percentage difference. And so these points are the mean squared error percentage differences for these Henderson MA choices. And you're not seeing any out here for the longer filters because I've capped the vertical axis at 50%. So I did compute those, but for these longer Henderson MAs, the mean squared error differences were bigger than 50%. So there was a big difference between the Henderson MA estimates and the optimal model-based estimates for these MAs. We see the mean squared error difference is minimized here for the 9-term Henderson, and it's a little less than a 10% difference. So that's a very good approximation to the optimal model-based estimate. The 7-term and the 11-term do pretty well too. When you get further away than those, then this difference starts to become substantial, and then it goes off the chart for the longer filters. So this shows for this particular case, if we do the 7, 9, or 11-term Henderson, we get pretty good results if reality is somewhat close to the airline model trend and irregular components for these parameter values. And when you get further away than those, you start doing worse and very substantially worse. Now, as we go to the other parameter values, here where the theta 1 is 0.5, notice that this sort of curve shifts. And now the best choice of Henderson MA is the 15 term. I think the 17 is very close. The 13 and the 19 and the 21 are also close. When we start, and again, it's about a 10% increase in mean squared error. When we get beyond those, it starts going up and goes up substantially. If we go over here to where theta 1 is 0.8, which is an unusually high value, but if we go to that, then the curve shifts again further. The best choice here was my upper limit of 35. So if I had let the Henderson MAs go longer, presumably, I didn't compute this. Well, I did try up to 39, and it did go down further. So it sort of looks like if you push this theta 1 higher and higher, you're going to get longer and longer for the best choice of Henderson trend MAs. Now, this is for symmetric Henderson trend filters in the non-seasonal case. Here's the concurrent filters. And now I'm going to start pointing out just general characteristics here. Again, the two rows are very similar, so we only need to focus on one. The seasonal MA parameter doesn't matter much to this. And again, as we go from left to right, the curves shift to the right. So as the theta 1 increases, longer Henderson trend MAs are appropriate. But a couple of differences, the pattern of the curves is a bit different, but more importantly, the dotted line here, which is at the minimum value here for the 9 term, is very low. So the percentage increase when you use the best choice of Henderson MA compared to the model base in terms of mean squared error is only, I don't know, it's 3% or something, so really negligible. This makes sense because what's happening is that a fair amount of the mean squared error for the concurrent filters comes from forecast extension, and both the model-based and the Henderson concurrent that I'm constructing use the same forecast extension. So they both get penalized the same amount of this additional mean squared error for the concurrent versus the symmetric filters. Now, here's the middle rows from the previous 2 charts, pages of charts. The top row for the symmetric and the bottom for the concurrent. And the point here is if you compare the two, you can see that where the mean squared errors are minimized for the symmetric and the concurrent is just about the same in, for the symmetric and the concurrent. So that's good because it means we don't have to worry about do we need to make different Henderson MA choices for symmetric versus concurrent filters. The answer is no, for the most part. So those are the results for this non-seasonal case, and I'm running out of time. Let me then skip to adhere as close I can to the time limit. A lot of the results for the seasonal case were the same. Here's the exception, and now I got to show all 3 rows. For the seasonal moving average parameter values of 0.5 and 0.8, the rows look the same. They don't when the seasonal moving average parameter is 0.2. Notice that here the minimums are occurring at much longer Henderson MA filters. That's a substantial difference between the 2 cases. I'm not exactly sure why this is arising. I have a suggestion, and I'm kind of troubled by this, but I'm not entirely sure what to make of it. Here's graphs of the best filter choices. This shows what's going on with theta 12 equals 0.2.
Hey, Bill, I know you're paying attention to time, but I promised to let you know when you had 2 minutes. So anyway, thanks.
Oh, okay, I got 2 more minutes. So I can get to my conclusion. So these are the best Henderson MA choices. Here for the symmetric and here for the concurrent. And the circles are the full seasonal case. The dots are the non-seasonal case. And we notice that when theta 12 is 0.2, the choices diverge substantially. They don't diverge so much for 0.5 and 0.8. Here they coincide where they're hitting the limit of 35. But this is the difference between the two. I also compared these to the choices of Deputeau and Planus that didn't do all the same parameter settings, but this shows what they got. This is for the seasonal case. And the dots are the Deputeau and Planus, so that they're missing 0.1 and 0.3, but they've got the rest. And you can see that they picked substantially shorter Henderson MAs. They also had a limit of 25, which, you know, from the results you've seen previously, it seems to make sense to go beyond that. So there are some differences here from what they chose. So in conclusion, we see that the best choice of Henderson MA can provide a good approximation to the optimal model-based estimator of a trend component coming from the canonical decomposition. The increase in mean squared error was about 10% for symmetric filters and very small for concurrent filters. And nearby to the best Henderson MA choices also did well, but if you got very distant from it, the mean squared error could go up substantially. We saw this odd result where the seasonal and non-seasonal cases in terms of the choices don't agree. We saw that longer Henderson MAs are better for larger values with theta 1, and that the value of theta 12 typically mattered little to the best choice of Henderson MA, was the one exception noted. So thank you for your attention.
Thank you, Bill. That was really interesting. We're going to hold questions until the end. So if you have any questions, don't forget, or you could go ahead and put them in the chat.